Talking about how we can do separation variables to adjust rotation on the sphere. So what we're bridging is from the rotation on the plane, and then we move up, add additional variable in the theta direction. So you really can consider, this is a problem, is really looking at the rotation on the plane, a stacking of the rotation on the plane across the theta angles. If we can consider about this, and that is the whole point. Did you guys see the updated lecture notes? I promised and I posted the updated lecture notes. And that's how we can play into the Schrodinger equation and trying to solve by separation variable. Because if you think that the system is a whole stacking of the 2D rotation, then the wave function can be tried as a product. Right, so you're thinking the wave function as a theta and phi. If you think it's a stacking of it, then we shouldn't be able to have a function that is related with the 2D component, and then you add the theta, which encompass for all the theta angles, and that's what we accomplished. We went through it. We can separate the Schrodinger equation into two equations. Each of it carry one variable. So instead of a function that depends on two variables, we can separate into a product of functions. Each one of them only depends on one variable. And if we take a look at it, we are successful because the first equation is really related, although we use a phi to represent, that is really the wave function solution. So that is really the wave function solution for the rotation on the plane. I mean, as illustrated here. So therefore, we already know what the solution is. The wave function for the rotation on the plane, you have a normalization constant, then you have E, then you have the E function that is a complex function raised to the negative I m sub phi. And then we have a solution for the wave function that related with the theta angle. Now, these two, the theta function here is a link from the m sub l, or from the rotational on the plane. Because if you look at the equation number 2, you have the m sub l quantum number indicated in that expression. So therefore, so you can solving for this, also impose the boundary condition in this theta as a two poles. So we will introduce, by solving the wave function for rotation on the plane to satisfy the cyclic boundary condition, we introduce the quantum number m sub l. Okay, now same thing, if you do the boundary condition related with the theta, we also have to introduce a quantum number to constrain, to satisfy that constraint. And that's why we introduce another quantum number that is L. All right. Now, by solving those two individually, however, solving for the theta, there's a link to the m sub L. So there's a constraint what m sub L value going to be. Depends on the L. So by doing this, we said, solving for the whole thing, we will have the L can take any, I'll give you the exact values. So the L is a non-negative integers. All right, so you have two variables satisfied with two boundary conditions. We will have two quantum numbers. One is L, the other one is m sub L. Now they are not independent. Remember when we do the translational motion, in 2-dimensional or 3-dimensional, we have a quantum number n1, n2, and n3. They are independent. Independent means they can choose their own value, does not correlate or dependent on each other. However, for the quantum number for the rotation on the sphere, we will have two quantum numbers, m sub L and L. They are linked. So L can take non-negative integers. Under each L value, we will have 2L plus 1 numbers and sub L values. Okay, so what does that mean? If L equal to 0, how many values for m sub L I could have? It's a 2L plus 1. That means I'm only going to have one value for the m sub L. Now, what value going to be? The value of the m sub L is also an integer. It's taking from the negative, it ranges from negative L to positive L and anything in between by stepping by one value. Okay, now let's give it a shot. So the m sub L can take a range starting from the negative L, which here L value, guys, is 0. So just for the sake of practice on earlier, from 0 to negative 0. Do you have anything else? No. So what the m sub L value going to be? 0. Only 0. What value? The value is 0 for the quantum number of m sub L. Now, what if L equals to 3? How many values of m sub L would we have?
7.
7. What are they? So I'll have negative 3, positive 3, then anything in between, then I'll have, right? So I'll have very, very good. Excellent. Now, we're skipping all this solving for that equation number 2, but aesthetically, you guys already know if you took it. So here, let me show you the wave function solutions, okay? Now you were like, oh, why do we use a y? I mean, gee, the book was using the, wave function. We use c as a wave function, but in this textbook, instead of the c, it uses a y. The reason for that is they want to save this to the later when you're including the radius as a variable. So basically, this wave function to this rotational sphere only depends on the data defined, and the solution of the wave function, we can call it as a spherical harmonics. We use a y as a symbol because it only depends on data defined. There is nothing fancy, okay? Now, depends on two variables, we need to introduce what? The quantum number, okay? So this is the same as you do rotational motion on the plane. You have a quantum number with the corresponding variables. Then you have the vibrational motion, you have a translation motion, you have a symbol for the wave function, indicate the variables, indicate the quantum number, because the quantum number is going to tell you the exact quantum state. Okay, now I said we were successful trying to use a separation variable to solving for this rotation on the sphere. So literally, the wave function solution should be a product of the two components. One component related with the data. The other component is the solution for the particle rotation on the sphere. Okay, now what we see here, under the each L value, you have a multiple m sub L. So the book gives you equal to 0, m sub L only equal to 0. So therefore, you're looking at what quantum state?
0.
You're looking at the quantum state 0, 0, because you have a quantum number to refer that quantum state, and there's a solution. So what is the wave function for the quantum state L equal to 0 and so equal to 0, guys?
Whatever it's applied to the
Huh? Root of 1 over 4 pi. That's a constant. Isn't that a constant? Oh, wow. Okay, so how about now when this is L equal to 0 and so L only equal to 0. So now the next one, L can take non-negative. So if we increase the number L equal to 1, then what M sub L value can be? M sub L can equal to?
-1, 0,
So how many quantum states do we have?
3.
We will have 3. Very, very good. So you have 1, negative 1. That refers to quantum state L equal to 1. And so L equal to negative 1. Then you have Y. 1, 0. Okay. And then you have Y. 1, 1. Is that all good? Okay. All right. Now, what is the value for this y1 negative 1? Everyone? Huh? What is it? Can you tell me what it is? Because that's important. Because for the translational motion, you have a generic expression, you just plug it in. As you see for the vibrational motion, it gets complicated. Same for rotational motion, it's complicated too. So the book only gives you the first batch of the solutions, but we need to know what they are. So if it's a y1 negative 1, what do we have? We already have a constant, don't we? What is the constant? Huh? 3 over 8 pi. Very good. And raised to the power of 1/2, excellent. And then you have the sine theta and e raised to the negative. Is that correct?
Is there a negative?
I think I missed something. What did I miss?
A negative at the front?
I missed a sign here, right? The book is sneaky. They combine the M sub L plus or minus into one generic expression. Isn't that what the book is doing here? You see the L equal to 1, M sub L equal to plus minus 1. They have similar formula, except the sign is different, depends on the M sub L values. So when you have a plus M sub L, it corresponding to a negative coefficient.
That's not our problem, it's a positive M sub L though.
Oh, yeah. Did I say negative corresponding to positive? It's opposite. It's opposite. That's the thing I want to make the point. You guys see this? You have the plus minus 1 for M sub L, but if I only want to take the negative M sub L, then the coefficient should be positive, and the E function should be negative because it's a plus minus. Are you guys following me okay?
Yep.
It's awfully quiet today. Okay.
So you're saying that the signs are flipped? So if you have a negative...
If you look at the expression, do you guys see the expression?
Oh, because it says minus plus, I see, okay.
Yeah, so it goes like plus on top, minus on bottom, and then it goes minus on top,
Do
plus
you
on bottom.
guys see this?
Yeah.
It goes back to plus on top.
I told you the book is tricky. So M sub L equals plus minus 1, okay? So refer to plus and minus M sub L, they group it in together because it has the same constant and expression, except when you have a plus 1 M sub L, it corresponding a negative sign in the wave function. Now, a corresponding E raised to the plus M sub L value. Are you guys following me okay? Alright, now how about the negative? Here. very straightforward. I'm only gonna do a couple of them for you. How about 1, 0? Okay, so this reason I wrote out the whole thing. Okay? Now the thing that I want you guys to draw attention is that we say the particle rotation on the sphere is a product of the particle rotation on the plane minus the contribution from the theta component. So we say we can do a separation of variable. Now can we see it here? Can we see that reflection here? So if it's a particle rotation on the plane, so when this is the wave function for the particle rotation on the plane that we already very familiar with, it only depends on the phi angle indicated by the m sub l quantum number. So if it's m sub l equal to 0, what will be the wave function? That will equal to a constant. Do you guys agree with that one?
Yeah.
Okay, now how about if this equal to 1? Then you have a normalization constant, and then times e to the negative. I don't know what's going on today with me. I flip the sign all the time from left to right. So how about with m sub l equal to -1? Do you guys, I mean, that's what we learned from the particle rotation on the plane. Do you agree with that one? Now, can you guys see it here? I have a component of what? Rotation on the plane, which equals a constant combined with the constant come from the theta. So that's what we have it here. So for anything when the m sub l equal to 0, sounds like it's vanished in that spherical harmonics oscillator solution. It's not, because it is a constant, so looped into the normalization constant for the y function. Now, if we take a look at plus minus 1 m sub l, I'm sure you guys can clearly see it. Can you guys see it here? Right, that is your product of the function rotation on the plane. Did you guys see this here? All right, and then you have an entity that related with the theta. So therefore, to demonstrate its separation variable really work, and our solution for particle rotation on the sphere contains the component with the rotation on the plane, and then you have the component related with the theta. Of course, you have the normalization constant. Okay, if you don't believe it, let's take a shot of this. So when L equal to 2, when m sub l equal to 0 is a constant, then it's related with plus minus 1, e raised to plus minus I phi, and then you have the m sub l equal to 2. Did you guys see the I m sub l phi right there? Make sense? Okay, now, if you guys want more complete for the class, they have more. But this is basically saying that anything related with rotation on the sphere, we're now giving you a more complex function than that what is given to you. But if we have L equal to 10, L equal to 100, for sure, they are wave functions. But that we were not testing you, we were not using those functions for your exam. Okay, all right, so this is a wave function. I explained to you separation variable, how you can see the overall wave function. We call it spherical harmonics. We use a y to represent because only depends on the theta phi. I give you the range of those two variables. We said those are quantum numbers a moment ago, but now we're going to tell you it's a rotational motion. So the L quantum number has a specific number. It is an orbital angular momentum quantum number. Okay, so the L is angular momentum quantum number. Orbital angular momentum quantum number. Okay, so why do we say orbital? So, you know we have Earth and Sun. How does the Earth move? Right? So the Sun is here. The Earth orbits around the Sun. So has this orbital motion. What else the Earth has?
Rotation.
Huh? The spin by itself, right? The same thing I wanted to tell you. Right now, we're looking at the rotational motion for any objects, but pretty soon we'll reach to the rotational motion, or we want to understand the property of electrons in the atom. What does the electron do in the atom, guys? It orbits around the nucleus, so therefore it will have the orbital quantum number. What else does the electron have? The electron will have a spin. As a result of that motion, we will also introduce the spin angular momentum quantum number. So it's all related with the angular momentum, but one refers to the orbiting, the other one related with the spin. Okay, all right. Then what about M sub L? So we're talking about angular momentum. Angular momentum, if you have a motion in 3 dimensions. Okay, so when we say angular momentum, this is an observable, which means you can measure it. Okay? If it's observable, what symbol do we use? In physics, what do we use?
The omega.
No.
No?
I said it's. Did I respond too quickly?
Oh, L. Sorry.
No. If it's observable for angular momentum in physics, oh, what is it, guys? Come on. J.
Oh,
J.
no.
J. Excellent. There's just so many stuff, right? So it's like angular momentum as observable. We use a J to represent J equal to something. Now, if we want to make it as the operator, what symbol do we use? That is, we use L with the operator notation. So observable use a J, operator use an L. Okay, clarify this. Now, if I'm having stuff that rotates in a 3-dimensional space, the angular momentum would have components in x, y, z dimension, right? That's the same as the kinetic energy, as the linear momentum. The value have a motion in x, y, z component. Then we will have a corresponding operator related with what? Those 3 axes. Right, I have a point to go to, but I need you guys to say, okay, I got it at this moment. Oh, I have a question. All right. Then, in quantum mechanics, what do we have? Wow, I didn't know today I'll write this far. We will have a quantum number. Okay? The quantum number to refer the whole angular momentum. What letter should we use? The cheat sheet. Right there. What is it?
L.
L. L can take
Positive numbers.
no negative values. Very, very good. Excellent. one more thing that I'll be done, I promise to move on this slide. Now, what if I have a quantum number for the angular momentum in one of the axes? Which axis we're interested? We're interested in the total and one of the components. Traditionally, don't ask me, we're interested in the z-axis. All right, if it's a z-axis for the orbital angular momentum quantum number, what letter do we use? M sub L. So M sub L, oh, can you see it? So M sub L refer to the quantum number for the angular momentum in the z. You guys, are we all clarified? So those are, we're talking about different things. We're talking about observable values, magnitude. We're talking about, we can use quantum mechanics, we can change an operator, we play into the wave function, we can do that, and then we have a corresponding quantum numbers right here. Now the z component, it doesn't look like reflected here. We're talking about magnetic moment. Magnetic moment quantum number really refer to the z component of the angular momentum quantum number. The same thing. Although sometimes same, we give a fancy name. Are you guys following me okay? The magnetic moment quantum number, it is nothing fancy. It's just the z-axis of the orbital angular momentum, okay? Now I can dive in. Why are we only interested in the total as one of the axes? Why are we not talking about the total and every single axis for the component for every single axis? Why not?
Because it's a sphere, so you have symmetry.
Okay, what else? What else? Okay, good try. Yeah. What else? What do we see? Is that what you want to tell me? So if we take a look at it, if you look in the Heisenberg uncertainty principle, evaluate whether you have two observables can be simultaneously determined with a certain precision. We introduce this one operator at the beginning of the discussion for rotational motion, and we evaluate the commutator between pairs between different axes, and pair between what? The total, right? This is the angular momentum operator for xy, yz, zx. Do they commute?
No.
They can't commute. So that means we can determine both components with precision. You guys agree? Okay, now what do you see here? You have the commute property between the total angular momentum with what? One of the components. They commute. So therefore, we can precisely determine the total angular momentum with one of the z component or one of the x component or one of the y component. So in that regard, we can choose one. So traditionally, we can use a z, okay? Okay, all right. Very good. So in that regard, we show what the wave function looks like. Now, can we calculate the energy? So this is an energy expression. Once we have the wave function, the spheric harmonics solution, plug back into the Schrödinger equation, and then we get the energy expression. Because the wave function was indicated by two quantum numbers, so we say, okay, the energy will have L, M sub L, and then it equals to L, that's a quantum number, L plus 1, and then H bar squared over 2I. All right. So this is the solution for the energy for the rotation on the sphere. Although quantum states are defined by two quantum numbers. However, for the energy, what do we have? You have a constant. I is the moment of inertia. I equals to m squared. So for a system, this is a constant too. So the energy only determined for a particular system by which quantum number?
Angular momentum.
Angular momentum quantum number. Now, if you look at as pairs for the expression for the wave function and the energy, can you guys see the degeneracy? Because what is the definition for degeneracy?
Two
You have
states.
n quantum state corresponding to one energy, that is your n-fold degeneracy. Okay, now the question, you guys know where I'm going. What fold of degeneracy do we have here?
2L plus 1.
What fold of degeneracy? You look at here. Oh no, I have the solution on the slide.
Yeah.
That's terrible. Is it a 2L plus 1 fold?
Yes.
How do we know that? Because under each L value, I would have how many values for M sub L? 2L plus 1. They all corresponding to the same energy, so therefore the degeneracy is 2L plus 1 fold. So that means when L equal to 0, what degeneracy do we look at it? 1 fold. When L equal to 1, what the degeneracy do we look at it? 3 fold. When L equal, okay, very good. All right. Okay, and then of course you have an energy expression. Now, what is the minimum energy? That's what usually at the ground level, right? So, what is the minimum energy? So you look at the expression. Positive, positive. Only depends on the L. L is non-negative value, so the lowest energy would be when L equals to 0. So therefore, this whole thing equal to 0. So then when if we evaluate the energy expression, we know the minimum energy will corresponding to L equal to 0. And I can plug it into the expression that give me 0 value at the ground state. Now when L equal to 0, that's the energy. Then what is the ground state wave function? Then we have to think about it. The wave function is determined by those two quantum numbers. So if L equal to 0, what will be M sub L value? 0. So I'm looking at the wave function of right, when we're looking at the wave function of 0, 0. And then I can look at the table, so I know exactly what this ground state wave function is. Root over 4 pi. So if I say, guys, give me the ground state wave function for rotation on the sphere, then you know right away that corresponding L equal to 0, S is L equal to 0. That means this has the same value at all theta and phi angle. Okay, all right. And then, all right, are we all good on this aspect? It's good? Okay, I'm very good at, challenging you guys. Okay, so now we know the energy expression. So what would be the kinetic energy, guys? This whole thing is your total energy, right? Solving for the Schrödinger equation, that is the expression for the total energy. Now what about the kinetic energy? Kinetic energy, is it a free particle? Yes. This is a free particle rotation on the sphere. So therefore, the kinetic energy of the system equals to at each constant state, the system will have a different total energy. And at each constant state, the total energy is the sum of the kinetic plus the potential, but the potential is zero, it's a free particle rotation, so therefore we can directly extract the kinetic energy. It's the same as total. Okay, we're not done yet. So in physics, how do we calculate the kinetic energy? Give me some expressions.
1/2 mv squared.
Very good. 1/2 the mass of the system times the speed to the power of 2. Now what if I want to know in terms of the linear momentum?
Momentum squared over
Okay,
2.
momentum squared over 2m, right? I'm not done yet either. What if I want to know in terms of the angular momentum? What about the angular? Guys, what about the angular momentum?
It's omega, right?
No.
No, it has an angular part in it, but it's an angular frequency. What about angular momentum? Oh, you guys can tell me, what about angular momentum? What is the relationship between the J and the P and the radius? What is that? Huh? You guys forget about this?
Yeah.
I'm in remembering things is hard.
Yeah, we're not really physics students. So.
No, we talked, I think we talked about it.
We did talk.
Oh, did you find it?
Guys, I'll be mad if I can't find the slide.
Would it be
That means
J
you guys think I didn't
squared
talk
over
about it.
Is it j squared over 2r?
That's what I was thinking.
Is it J cross
That's what I was
product
thinking.
You guys are thinking, I like it, right? So therefore, I don't want you to remember it, but it's a relationship because J and P are linked. So I can substitute P with what? J and I. Very good. So what do I have in here? It's the J over R squared 2F. Any questions on that one? Because P equals what? J divided by R. But come on, you're gonna have to agree with me. Is that true? So I can substitute the speed with the linear momentum. I can substitute linear momentum with what? Angular momentum. And then get back to Jordan, your solution. What is it? You're correct. You go J squared, I put the R squared over the denominator, so what do I have? I just take one extra step to show, okay? All right, now what do we have in here? That equals J squared over 2I. I'm really not done yet. Okay, so, you guys all following me on this, okay? Good? Okay, so we have the classic physics, how to calculate kinetic energy. All right, now what are we going to do? We're very good at combine. So now look, the kinetic energy from the quantum mechanics perspective equals to quantum number at that particular state, then times the constant h bar squared over 2I. There's nothing fancy, isn't it? That will lead to, you're looking at the same thing. It doesn't matter you found the quantum mechanics or quantum mechanics, those kinetic energy has to be the same. So that will equals to J squared over 2I. Oh, that everybody should say yes, that is so correct, right? Is that true? Okay, now what I'm gonna get out of this? H bar, oh, fast. What do I have? I can get the J expression. What do I have? J squared will equals to L plus 1, H bar squared. I to I, same, L times L plus 1, H bar squared, J. So this gives us an idea how to calculate the magnitude for the angular momentum, or the observable for the angular momentum for rotational on a sphere. Because now, of course, we're giving a square. How am I going to know just the J value? It's a root of the quantum number L times L plus 1 multiply, that's not in the root, H bar. That is your magnitude for the observable for the angular momentum. Does that make sense? You guys all follow me okay? Alrighty. Okay. Now, let's say this system is defined by spherical harmonics of 0, 0. What will be the J value? If I measure the angular momentum, what will be the value?
0.
Of course it will be 0.
Okay.
Why is it 0? Because the J equals to
L. So G's not going to be 0.
from the quantum mechanics, knowing the quantum state, that's the whole beauty of quantum mechanics, that J can be evaluated, depends on the quantum state. Now what is the quantum state when you represent it by y00?
Constant.
L is 0. So therefore you have no angular momentum, no energy. We're all good, right? Now how about if I'm at the represented by the excited state, 181, then what would be in that particular quantum state, if I take a measurement, what would be predicted? Then the same equation represented by the value of the quantum state plus time L plus 1 H bar. Now what is L here?
1.
Huh? 1. So the value will be root 2 of H bar. So I show you, once we know the quantum state, how we can measure the total energy, what the kinetic energy looks like, what will be the interest for another observable, that is your angular momentum value. Okay. All good? All right. Now what if I don't care about the total angular momentum? I'm only care about the zeta. Like this is the total. This is what? The total. Right? Is that true? But I only want to know the magnitude for the z component. How should I do it?
We use the ML value.
Then we can evaluate the operator as we wish, right? I mean, if I want to know, basically I want to know what the JZ value is. then I can come up with an operator to evaluate on that. Okay, now what is the operator for the in the z component? Right?
It's getting it more.
I have it.
So it will be
H bar over I times the derivative.
with regarding to the variable of phi a. I really wish somebody can tell me now what would be the z component of the angular momentum? Now this is only depends on the phi variable. The wave function for rotation on the sphere is a product of the components from the rotation on the plane multiplied by the function that related with the theta. Now, if we do evaluate with respect to the phi, do we care about the theta component? If we do not care, if you do the operator onto the particle effective rotation on the plane, then what will be the magnitude for this?
Hmm?
Is it true or not, guys? Is it true or not?
111?
Even if you think it's not true, I'm telling you it's true. Right, we're talking about the angular momentum value for rotation on the plane that only have the z component, and we know it depends on m sub r h bar. Now you have a rotation on the sphere, you can have an x, y, z component. So this is giving you the total. But in the z component, if you look at the operator, only depends on what? The angle phi. Phi is really our wave function for rotation on the plane. So therefore, your value for the z is really the m sub r h bar. Alright. Okay. If that is established, then the question that I'm having is, when L equal to 0, quantum number. Or let's say you have a quantum state 0, 0. What would it be the value in the z component?
0.
That is represented by m sub L h bar. M sub L is 0, so therefore it is 0. Now what about for this particular one? Then the JZ equals m sub L h bar.
So negative H bar.
Then you will have what? Negative h bar. Very good. Very good. Okay. Now, one more thing. One last thing. Okay, so I say for quantum state L equal to 2, the quantum number L equal to 2. What would be the measurement for the observable J values? That will be
Negative H bar.
root of the quantum number L times L plus 1 h bar. Then what do you have? The magnitude was equal to root of 6
H bar.
h bar. That's what you're going to measure. How about the z component? The z component that equals to m sub L h bar. Yes? Now how many values what do we have?
5.
Wow. I think you guys deserve to leave early today. That is, what are those 5 values?
Negative 2 H bar.
0, negative h bar, negative 2 h bar. Excellent, excellent. Okay, sounds good. So I'll post the lecture notes for the chapter 8. We don't have a homework this weekend, right?
No.
So,
At least